Hi, this is Robert Quimby, and I'm going to tell you about working with FITS data in Python. So in this tutorial, we're going to learn a little bit about the FITS standard itself, this data format for encoding information into files. We're going to actually download some FITS data files, some FITS images actually, and we'll take a look at those, the structure of the file. Then we're going to do some work with Python. So we're going to actually load these FITS files into Python, and we're going to look at the headers, and we're going to look at the data. And it's going to include actually displaying the images. We're going to use matplotlib to do that. And we're also going to use this tool SAO image DS9. And DS9 is a standalone package. It's separate from Python itself, but you can use some tools in Python. There's a Python package so that you can actually control your DS9 session. So we're going to go over all that. So first, let's just talk a little bit about the FITS data standard itself. This is the Flexible Image Transport System, and there's a primer for this supplied by NASA online. This will tell you about the basics of the format, but what you generally need to know is that this is a data format that was invented a long time ago. Basically, the late 70s is when this originated, and it's a file format that was developed so that astronomers could take data from the mountaintops where they were observing back to their institutes. That's why it's a image transport system, because the data was being transported in media from one place to the other. This is very flexible. The F in the FITS is very apropos. It's this data format has survived all these decades, not because we're just stuck with it, but actually we're lucky to have it. It's very flexible. We can use it for many different things. We can use it for displaying images, but we can also use it for data tables. It has a wide variety of applications, and it is just ubiquitous in astronomy. So very, very handy format. The way a FITS file is structured, this is a graphical representation of that. Essentially, there are blocks of data. This is a series of bits, if you like, of data of a certain length, and there has to be at least one of these blocks. This could contain several sentences of data. You can think of it that way. Then there can be optionally other blocks of data. And these first blocks form what's called the header. This is information about the whole data file usually. This again, it's a flexible format, so there's other things you can do with it. But in the typical use, the header is going to tell you, it's going to give you metadata information. It's going to give you data about this data that's stored later in the file. So it could give you, for example, if you have an image, it could tell you how big the image is, how many X and Y pixels you have. It can tell you when the data were taken. It can tell you who took the data, what telescope. All sorts of information could be stored in this header. And then after all, you have all these header blocks. There is optionally this data. So again, you don't have to have data. It's a flexible format. But if you do have data, it would go here. So this first part of this data, shown in these blue blocks here, these header blocks are in the ASCII format. So they're simple, basically you can read them, your human readable format. After you get into the data can be encoded in binary. So it's not something you can see. It's not going to be numbers that you can understand if you look at the data. But the information you need to take this binary information and transform it into numbers that you can understand is stored in the header here. And we'll see how that works. So this is kind of the standard FITS format for a typical image. But again, this is a flexible format. It has been, the format has been changed over the years to be more and more general. And one of the changes made a while ago was to actually add what are called extensions to this FITS format. So in this single FITS file, you can have your header and optionally some data, and then you can have another header and data, and another header data, as many as you want. And the advantage here is that, say you have a set of images that are related somehow, like maybe you have images taken over time of the same field. So you can put all of these images into one data file and just and store it together. So often when you do that, if you have multiple extensions, usually this primary header, header data unit, that's what HDU is here, your header data unit, has no data. Usually it's just the header information only. So you'd have this header information, and then you jump right to the next header and data, etc. But you could have data if you wanted to. It's a flexible format. All right, so it's probably best to actually show a real example of what this file format looks like. So to do that, we need to get ourselves some FITS images. And a nice way to do that is to go to this online archive. So this is the Space Telescope Science Institute's Digitized Sky Survey. And this is a nice service, because what they have done is they've taken images that were taken decades ago, some data taken in the northern hemisphere and some in the south, that cover the entire sky. So you can put in the right ascension and declination of any spot on the sky, and you can pull an image of any size up to 1 degree on a side, and you can download that data in the FITS format if you like. So let's go ahead and do this, and you can actually use this little object finder up here, and it'll query Sinbad or Ned to get the coordinates. So we can ask it for the coordinates of NGC 891. This is a nice galaxy, and I'll click on Get Coordinates, and it puts in the coordinates here, the REN deck, and then I can click down here and Retrieve Image, and it's going to download a FITS image. It's going to, by default, go to the POS2 red, and it's going to download that for me. So I will retrieve this image, and here it's downloading. It takes a little bit of time, and there we have it. Our image has been downloaded. So I'm going to now take a look at that image. I'm going to go to my tutorials directory here. By default, this image is going to be saved to your downloads directory, of course. And the name of this one is going to be DSS search, and then in parentheses 1. This is because I already have a DSS search, so this is the second one I'm downloading. So I'm going to copy that. Actually, I'll move it. It's in my home directory, that's what the tilde is for, in downloads, and it's called DSS search. So if you've never downloaded WIMS before, that would be the complete name right there. But for me, there's a space and then the number 1, like that. These slashes, by the way, are just because these are the escape keys. So if I have a space here, I want to tell it that that's part of this whole name. So I put a slash there so it knows that this is not a separate token from this, that this is one token here. So I will move that, and I'll rename it just DSS search .fits, because it doesn't have this fits ending, and that's the standard ending for fits files. So there we have our DSS search.fits file. Okay. So we can take a look at this file if we actually just use the less command and we pass it this fits file. We can see that header. So this is what the header of a fits image looks like. They must have this keyword here. So this is the structure of this header is that there's keywords here, the first 8 characters. There's an equal sign, and then there is some value. And then you can put a slash, and then beyond that slash there's a comment. So the first keyword is simple. Its value is the capital T. That's the Boolean representation for true. And then there's a comment that says this is compliant with the fits format, basically. All right. The next 4 keywords here are telling us something about the data that are going to be in the file. So this is telling us there's going to be data right after this header, and there's going to be data represented in 16-bit format. So this is telling us that when we're reading that data file, we have to read 16 bits of information before we have 1 pixel. All right, and there's 2 axes. Right, there could have been 3 or 4 or 1, but there's 2. And the first axis has 891 pixels, and second has 893 pixels. So this information is critical also for decoding this image. So if we go back to this representation of the fits format, so I'm looking at the first block of this header here, and it's telling us that when the data starts, that we're going to have to read 16 bits to get 1 pixel, and then we're going to have to read 891 more pixels just to get 1 row, and then we're going to have to do that whole thing 893 times. So that's telling us how to actually construct this image, because this data here is not stored in any kind of 2-dimensional fashion. It is stored in one long string. So the header actually has to tell you how long that string is, how many bits per pixel and how many pixels you have. Okay. So there's some other information here. By the way, you might notice something interesting. This is all, like I said, one long string, and that includes the header block and the data. It's all one long string. It looks nice here, but that's because there's 80 characters per line. If I change the size of my window to something that's not 80 characters, suddenly it looks like a big mess. But if you turn it back down to 80 characters wide, and by the way, you can look up here at the top bar when I move it. If you look up there, it tells you 80 by 26, 81 by 26, 82 by 26. That's the size of my terminal. If you get it 80 characters wide, then everything lines up perfectly. But it's really just one big long string. So that's why if I double click, I get this word, and if I triple click, I get the whole line. And look at that, I'm selecting everything because it's one line. Okay. So that's what the fits file looks like. So I just showed you the header. Let me show you the whole thing. So that's the header, and if I keep going down, these are all keywords in the header, everything in the header. There's an end statement, and there's a bunch of blank spaces where it's still going to the end of the block, right? So this block is not necessarily one line of the header file. It could be several lines. And so if this end statements come somewhere in the middle of a block, it's got to have blank spaces all the way to the end. So there's still a bunch of white spaces out here that do nothing, but they hold space. And then eventually, boom, this is where the data file starts. So after that end statement, there's some white space, and then the data starts. And this is all not in ASCII anymore. This is now in binary format, but we know how to decode it. Okay, so that's what it looks like. How do we actually access this in Python? Well, there is a package in the AstroPy package that called fits. So actually, it's in the AstroPy IO package. So from AstroPy IO, import fits. That will, if I run this will import the fits input-output package. So now we can load and read fits data. So let's tell it the name. Let's just define fname to be the name of a file we want to download. So we can, we have this file here, this DSS search.fits, and that's in the directory I am right now. So I'll just do DSS search .fits. That's what I named it. It could be named something else if you are doing things differently. And then what we want to do is actually get access to those header data lists, right? So we have a method called open in the fits package that'll open a fits file, and it'll give us a header data list. So I'm going to call this HDU list, and we're going to fits open that file name, like this. And if we do that, you can see what we get is we get this AstroPy IO fits list. This is what the square brackets are, and it just has one element in it. It has a primary HDU. So it's a list, so we can access it like this, and this is just that first HDU. And this has members called data, which has the data, and header, sorry, header. So header, this is that data we were looking at in the header of the file, and that's just represented as a astropio.fits header object. We'll look at that in a second. And the data, we'll also see in a second, this is represented in a NumPy array, which is very convenient. There are some methods, actually, some convenience methods if you directly want to load something. If, say, you want the header from some known file, you can just use fits.getHeader and supply the file name. And that will load the header, just like we did using this HDU list. And by default, it's going to use that 0th extension. But you can say whatever extension you want. If it's the second extension or third, whatever. And there's also, you can load the image data, call that image, with fits get data, and again pass the file name. Right? So now we have our header data loaded and we have our image data loaded. Let's take a look at what we got. We already did this, but we have our head with our keywords and our values and our comments. These are stored in a special dictionary called a FITS.io header, AstroPy header. So we can actually look at the different keywords that are available to us in this special dictionary. There is in the head object that we just created, there is a method called keys. And if you just run that, it tells you have a generator object. And what this does is it generates this iter. It gives you each of the keyword names in the header one by one. So we can do a for loop with this. We can say for key in head.keys, print key. And here are all the names of the keywords that are available to us. Right. So now we can access the a given value. So say we don't know what the data obs is in the header. So we just take this header object and then we pass the data obs string. We can run that and it'll tell us this is the date that that image was observed. And I should add that this is not case sensitive. So if we say date obs with lowercase, we'll get the same thing. And you can, again, you can change this to capital letters. It really is completely case insensitive. Okay. Now the data is returned in a NumPy object, as we saw. We call this image. And there's our data right there. Since it's a NumPy array, we can do a lot of things with it. We can access the shape attribute to see how big this image is. And again, it's 893 rows and 891 columns. You might be wondering, isn't this the reverse order that we saw before? Well, this is correct, actually. So we have the rows. Those are kind of the horizontal lines across the image. And so that as you increase the row number, you're actually increasing the y-coordinate. And the y-coordinate, if you want to think of it that way, comes first in AstroPy, in NumPy array objects. So it's row column order. There's also all the usual functions, like if you want to know what the maximum value is in the entire array, there it is. It's 26,000. That's the maximum value in the entire array. Right? So all those tools are available to you once you've loaded the image. But what you probably want to do is you probably want to display this image. So there's one way to do this using matplotlib. So I'm just going to set up matplotlib in line. I'm going to import matplotlib pyplot as plt, and I'm going to resize the default figure size, change it to 10 to 10. So I'll just run this, and now we can actually display the image, and we can use plt imshow, imshow, image show, and we just pass it our image data, and it'll display it for you. So you can see what we're looking at is actually there's a nice pretty galaxy here. This is our NGC 891 that we requested. Nice big pretty galaxy. Now you might notice a few things by default. One, it's shown in some kind of a false color, right? This is actually just a simple grayscale image. It's not really a big green galaxy with a bunch of green stars and a blue sky. This is just the default color map that's being used. It happens to be those different colors. So we can change that. We can say we want the CMap to be gray, and then if we run it, we'll get something that's a little bit more traditional. Now, the next thing you might notice, if you look closely, you can see the column numbers here, the x-coordinates, increasing from 0 to about 890, whatever. But if you look on this axis, wait a minute, 0 is up here at top. And that might seem odd to you, but this is how typical images like JPEGs and PNGs and GIFs are represented. The 0, 0 coordinate is actually in the upper left, not the lower left. So if you want to change it to the lower left, which is usually how you look at a FITS image, you need to change the origin to lower. And then it'll flip it around for you. And there's 0, 0 down here in the lower left like it should be. There's other things you can do. You can actually change the scaling of this image. What's going on here is we have the black of sky and the brightest pixel in the center of a star there, there's a huge dynamic range between the absolute black here and the absolute the bright here. But your computer can only display so many shades of different brightness, right? So I mean, you can see this here between the numbers, the 4 here, the zeros, and the white background here. That's the dynamic range limit of your monitor. But it's possible to be brighter than this and actually darker than this too. So what do we do with image data where we could have actually a huge contrast between the dark of the sky and the bright of an object like a star? Like this could be orders of magnitude in brightness scale, where here we're limited to a range that's very modest actually. It's only we have numbers basically between 0 and 255 in shades of brightness, right, where these could be between 0 and maybe 60,000 in a typical FITS image. So what happens is there's a scaling that goes on between the actual data values here and what's actually plotted on this image when matplotlib runs. So we can change those values. There's keywords vmin and vmax, and we can change vmin to say 0 and maybe vmax to some number like, I don't know, 3000. We'll see what this does. And that's made everything white, so apparently we should pick a larger value here. We remember it went to, I think 26,000 was the most. So let me run this. There we go. So what we're doing is we're changing, vmin is saying what is the data value that we want to call black. So data values of 0 or less are going to be drawn as black. And what is the data value we want to be drawn white? So data values in our image of 10,000 or greater are going to be drawn white. So now we see that whole galaxy basically is drawn in white because it's brighter, and our background is now in a shade of gray. We can change the vmin to some other value, and we'll make that background darker. Like that. Okay. So this is nice. If you're working in Python, you can do things here, but it's kind of limited in utility. It's not really easy to do things you want to do. Like you want to know what's the coordinate. I'm pointing to the cursor, and you just want to know that right away. So there is an external FITS viewer that's very handy for this, and that is called SAO image DS9, or usually just DS9 for short. You can go to the DS9 website down here, and they'll tell you all about SAO image DS9. You can, I guess, subscribe to their Twitter feed if you care for such things, and this will tell you give you documentation of all kinds of things that you can do with DS9. I'm just going to show you a little bit of what you can do with it, and then I'm going to encourage you to explore on your own to find some new things. So here's just a rundown of what you can do with DS9. You can open a FITS image. You can actually open up multiple images at the same time and show them in different frames, or you can tile them on the same screen. You can view the header information. You can play with the contrast to change that black and white limit like we just did. You can pan and zoom around the image. You can add symbols and text to the fields and mark things. You can do some analysis. You can load some online catalogs and say where are known stars, for example. And you can do some basic analysis like how bright are objects compared to other objects and where they're located. So let's go ahead and do some of this. To do that, let's actually launch DS9. So I've already started Astroconda, so I can just launch DS9. And I'm going to put an ampersand to do it in the background. And I will get this window right here. So here's my DS9 session. And I can load an image using the File menu. Let me actually just first orient you because there's a lot going on here. So when this window pops up, you'll notice there's a row at the top. These are menu items. Your standard, you click on it and the drop-down menu pops up. File, edit, view frame, all that. And then there's it's an information pane, and there's these little windows here that have nothing in them right now because we haven't loaded an image. And then you'll see the File, Edit, View Frame buttons again. So this is looking similar to this, but these are not drop-down menus. These are buttons, and if I push these, the row of buttons below it changes. So I can do File. So somewhat inconveniently, these aren't mapped perfectly. Like if I select File here, I can see that I have the choices to open and page setup and stuff like that. and there's open and page setup, but there's no like import. That's not shown here. So it's not perfectly map one-to-one, but some of the most convenient things are going to be down here. So I can file open, and I can open that image just by double-clicking on it. And here's that image I downloaded. And so now we can play around with a few different things. So one of the first things you might want to do is to see the full image, because you can see we're actually just seeing a crop view. And that's demonstrated here in this little window here. This is showing you your overview. This is the entire image in black. In this little blue region here, this is showing you what's actually in the main display here. And if I change to the zoom tab here, if I click on zoom, then I can actually zoom to fit, and I can put that whole image in there. And you can see the blue is now on all the way around here. Or I can zoom out further, make it small, or I can zoom in by a factor of 2. And again, you can see what happens in the pan there. When I move the mouse around, you might notice that in this window right here, there's a magnified view of whatever I see in the main window here. And the other things to note is that at the top here, it's telling me the name of the file I have loaded, some information about that. And then these are all blank now because my cursor is not on the window, but when I move to the window, it's telling me the value of the pixel. It's telling me the coordinates of this pixel on the sky in RA and DEC. It's telling me the physical coordinates in X and Y, and we're looking at frame number 1. We can add other frames if we want and add other images just with the frame new option. But what I want to do now is to actually show you the header. So I'm going to go back to the file menu, and I'm going to open the header, and we can see this. We can see the header information that we've been looking at before. So that's available to you just from File, Header. We can change the contrast and scaling. So if we use the Scale button here, by default it's doing min-max, which means it's finding the lowest pixel value and it's assigning that to black, and it's finding the brightest pixel value and it's assigning that to white, and then it's using grayscale linearly interpolated between those two. I can change to what's called Z-scale, and this is pretty handy. If I zoom to fit, this is a nice way to display images when you don't have one dominant image like this. If you do have one bright image, min-max works pretty good, and that does good, but usually you might be interested in something over here, and right now I can't see anything there. It's too dark. But if I Z-scale, I can see, oh, there's a whole bunch of little objects over there. There are many options for how you can change the scale. They're not all shown on the buttons, but if you go to the Scale menu, you can see you can change the scale in a variety. There's min-max, there's Z-scale, and then there's these other options that limit where the brightest pixel is set, like that. So the best way to see this is actually to go to scaling all the way down to scale parameters here, and it'll pop this window open. And this window is showing you a histogram. This is a log scale here, but a histogram of all the pixel brightnesses on the whole image. And the red line is where it's setting the black level, so everything less than this is going to be a black pixel, and everything greater than this is going to be a white pixel. So everything greater than 2000 right now is going to be displayed white. You can click on this and drag it and put it over here, and that'll change. Everything brighter than this pixel value is going to be white. So that's why you see suddenly there's a lot more white pixels when I do that, and I move it over here, there's a lot less white pixels. Same thing for this edge. This determines what's black, so if you want to make a lot of things black, you can move it that way, and that'll increase that. If you want to make nothing black, you can do that. Now the background's white. So if you do these default values like 99% here, you can see what it does is it sets the black value, and then it sets the white value to include 99% of the pixels. So sometimes those are handy, but I like Z-scale is probably the most convenient in general. Okay. So some other things you can do, I showed you can zoom in and out. We can also make some marks on this image. So you might want to highlight a star. Maybe you like this star right here and you want to draw on it. And you want to put a circle around it, I should say. So you can do that by going to Edit, and by default your editing is none, which means when you click on the image, nothing happens. But if I change this to Region, Now when I click on an image, it puts down a circle by default. And I can click again on that, and it'll put those little squares there to know that I have this captured. And then I can use the mouse keys, and I can move this around like that, and I can center it up however I want. And then if I double click on this, it'll pop up this little window, which tells me information about this circle I've put on here. It tells me where on the sky I've put it. This is the RA index of that circle. It tells me the radius in degrees. And maybe degrees isn't very convenient. Maybe I want pixels. Well, I can click on this, and I can go down and say I want it in image units, and then that's in pixels. That's 37 pixels wide. And maybe I don't want the RA index displayed like this. Maybe I want it to be not in sexagesimal, which is the degrees, minutes, seconds, or hours, minutes, second format. Maybe I want it in decimal degrees, and I can change it like that. Or I can do it in a different system. I can have it in ecliptic coordinates if I wanted to, or in B 1950 coordinates if I really wanted to. But sexagesimal is usually pretty good. So there's a whole different types of regions that you can plot on here. By default, if you go to the region menu to go down to shape, by default it's doing circle, but you can plot boxes if you want, or polygons, ellipses. One thing it's useful sometimes is the projection. So I can plot a projection, and then I can draw a line from one spot to another, maybe like this, and then it'll pop up a projection of that. And what this is this is just a line right now, so it's just the value along that line across the image. And if I click on this, I can drag this middle part here, and then you'll see what it does is it's actually now taking an average across this whole width of this rectangle that I've drawn here. So it's the average value, and that's handy if you want to know. Maybe you don't want that galaxy, but you're just looking at the background and you're trying to get some handle on what the background level is. You can see it's around, looks like, we can zoom in actually. If you click on this, you can zoom like that. And maybe I think this is the background here. So it looks like the background level is around 4,450, something like that. And then if I want to return, I can right click, and that'll bring me back to the top level plot. You can zoom in step by step. All right, so there's a few more things you can do. One handy thing you can do is you can open up a comparison image. So if you go to this analysis field here, analysis menu, you scroll down to image servers, we can directly load images from the DSS. So I can follow that link there. And by default, again, it's going to give you the POS 2 red, but let's say we'll do the POS 1 blue, just to be different. And I can retrieve that image. And there we have it. Now it's downloaded this, and you can see now it's displaying two different frames at once. This is my frame 1, this is my frame 2. You notice this value here changes as I go from frame 1 to frame 2. If I just want to see one of these at a time, I can actually go to frame single, and it'll just show me this one at a time. And I can switch between these two by hitting Tab key. That'll go between these two. And you can see that there's some rotation in this field. That means one of these images was taken at a slightly different angle than the other. If you want to align these, you can actually go to frame. It's got to be on the menu on the top here. And you can either go to match or lock, but I recommend going to lock, frame, WCS. So this will lock the images by their RA's index. So if I tab between these two now, you can see that these images are now been aligned with north due up, east to the left. Okay. So one last thing that we can do with DS9 is we can actually overlay known objects. So if I go back to analysis and go down to catalogs, I can go to a database like NED, and I can say show me where all the known galaxies are, or I can go to Sinbad and show me where known stars and other objects are, or I can directly search one of these databases like say the Sloan Digital Sky Survey Data Release 9. If I click on that, it'll bring up this window here, and this will retrieve images from the Digital Sky Survey. I think maybe there's nothing for this field because this is Sloan doesn't cover the entire sky. But if it did, it would pop up, and then we get circles for everything. So actually, let's pull up a different service. Go to Analysis, Catalogs, And I'll go to Ned, because I'm sure Ned has stuff in it. And we'll just ask Ned for everything it knows. And it's loading right now. It's the status loading. And when this is done loading from Ned, it's going to show you in the field everything in this field of view that is known to Ned. It might just take a second to load because, as you'll see, there's a lot of stuff in the universe, and Ned knows quite a bit of it. So hopefully it'll come up shortly. But what it'll do is it's just going to draw little circles around every object that it knows. It's taking, oh, there it goes. So you can see, in fact, it does know a lot on the sky. A lot of different things. So those are known objects. Okay, so I'll go ahead and close this. This is all great if you're happy to work in this with this little widget, but sometimes you want to control things from Python because you might want to do things programmatically. So I just want to show you now how you can control this window using your Python session here. So the first thing you want to do is you need to import the PyDS9 module. So import PyDS9. Try running this. If you don't have PyDS9, if it says it doesn't know what it is, then you can go back here and you can pip install PyDS9 and just run that. And then after that, you should be able to run this again. So I've imported DS9, and now what I'm going to do is I'm going to create an object that I'll call DS9, which is going to be a PyDS9, capital DS9 object. So I'll run this, and oh, I got more than one running, of course, just because I made things complicated. So if you run into this, the easiest thing to do is to just close this window, close all your DS9s, and then start over. That's the easiest thing to do. But if you ever find yourself in this problem, what you can do is you can figure out which of these DS9s you have running. So the problem is I probably have more than one of these windows open on my computer right now. So what I'm going to do is I'm going to ask it, go to XPA here and say, get information. And the one I'm running is this one, the A8241. So this one right here. Right. So I'm going to copy that, and then I'm going to put this in quotes in here. And now I run it. And now it knows that when I'm doing something with this object, I want to affect this particular session of DS9 right here. That probably wouldn't happen for you unless you were like me and had multiple DS9 sessions, but that's how you deal with it if that happens. Okay, so now there's a whole bunch of things we can do. First thing we might want to do is to display an image. So what I can do is use the DS9 command. So I'll take my DS9 object and I will use the set method, and I will set, in quotes, file to be the name of a FITS file. So I could put that DSS image if I wanted to, but in this tutorial, in the media folder, there is a file called example.fits. So I'm going to set that, and I'll make this window a little bit smaller so we can see what happens when I run this command. So when I run this command, it should set it, but it's not setting it anywhere inconvenient, is it? Well, I think what happens is I need to actually shut this down and do it again. Sorry about that. So I will close that window. I will try running this again. Now it's happy. Now when I run this command, I have DS9 somewhere else. Sorry about this. Do I have another DS9? Oh, I do, right here. I don't know where that is. Okay, I'm going to close that one. Okay, sorry about that. So now I'll run this. Boom, it pops up DS9 by itself. Okay, now it should have control. I'm sorry I had the wrong connection there. So if I run this command now, you can see what it does is it displays that image in here by automatically. Z-scale. So this is the example.fits image. There's other things we can do after we've displayed it. We can actually, I'll just comment this out and add another command. We can do ds9 set frame 2 if we want to open a new frame, right? And now I can set frame to 1 if I want to go back to the other one, and I can change the I can change the scaling. So we changed the scale to z-scale already. If I change the scale, if I want to change it back to min-max, I can do it like this, or I can go back to z-scale. And you can see as I make these commands in Python, it's changing this window here. I can actually also do zoom to fit. Oops, so I have to set zoom to fit, and it'll fit that window, shrink down the image to fit in the window. And one more thing that's sometimes useful, if you wanted to actually lock the frames, if you had two images and you wanted to lock the ARIA index like we did before, you can do ds9.set and then lock frame WCS, and that would do that. So these are just some of the commands you can do. You can play around with this, and you can probably figure out how to do other things. And there is a listing online of all these commands. So what we're doing, actually, these commands are called XPA commands. So if you look up ds9 XPA, it'll tell you all these different options for these commands. One more thing that we could do, we might want to put a marker somewhere on this. So maybe we want to highlight this star over here. That's around 728,606. So I'm going to define x, y, and radius, just r, to be, I already forgot. So say 730 and 611. That's close enough. 730, 611. We'll make it maybe 20 pixels in radius. And then we can use ds9 set, and we can use regions. This has a slightly different format, regions, in quotes, and then comma, and then another string. We're going to pass two strings this time, image, and we're going to tell it to plot a circle, and we're going to input the coordinates in just a second, and we're going to make the color green. And now we can format this string with the dot format. We're going to put in x into this first space here, y into the next one, and r into the third one. This is just going to fill in these blanks when it runs. And if we run that, boom, we get a green circle right where we wanted it. So one last thing is, we've been putting things on this image. We can also take information from this. If we want to get, for example, where the cursor is, like where is this object right here, we can ask it. So what we can say is ds9.get instead of set iExam. If we run this, see it's waiting now, nothing's happening. I go over here, you can see the cursor's changed. It's now flashing. And we can put this wherever we want, and we can click the mouse, and then it sends that coordinate back to our Python session. So these are a few of the things that you can do with ds9 and interacting with Python. There's a lot more to explore. I highly encourage you to actually put up an image here and then start clicking on these buttons and look at these options and look at all the things you can do, all this different analysis that you can do. Start taking a look at it. Look at the different shapes you can plot. Try some of these different menu items and see what they do. And enjoy.